Okay, this kind of only started recording now, I guess, and in the cloud. Yeah, this is. Yeah, I could almost. I could make this live to YouTube. Maybe I can do that. Start doing that because it gets immediately recorded.
Yeah. It would
I will start doing that. No, I will leave to. I will just stop Zoom on my laptop, but I'm afraid this recording will be lost.
Well, I would imagine it will take some time to save it, actually, like it happened last time.
Yeah, I know, but the thing is, it's still that's a few minutes. But the problem is not that. The problem is I will quit it. I will quit Zoom on my laptop because it's frozen.
Oh, like force quit.
Exactly.
Yeah, it's frozen, but your laptop camera is still streaming.
What is streaming is my tablet camera, I guess. No, but my
no, it's the laptop camera. It's 100%.
Can you see me moving?
Yeah.
Is it the cable?
Could you maybe you're logged as the host on the tablet? Yes.
I'm now a host on the tablet. Yes.
Could you kick the computer out?
I forced myself becoming the host. Yes.
Yeah, but okay. So now we don't see you anymore.
Now you don't see me. Okay. And I cannot do anything with the. Let me put again there. Okay. I will simply remove Zoom, quit Zoom, not removing Zoom, quitting it. In Ubuntu, it's it doesn't work like that. Okay, I will have to do force quit. Oh, this is hurting now. Okay, now I will get in again. My laptop. New tab. Okay, now I think I have to join what's going on here. I'm not joining audio. It's recording. It says recording. That's but maybe this is the recording on the. Yeah, this is.
Oh yeah, on the tablet.
Anyway, I will still record it, and then I will see what happens later on. So now I will share the screen. Okay. This is like the first year in this format. So next year I will do different things like use maybe immediately streaming to YouTube. Not next year, next time already. Stream directly to YouTube. Perhaps that's the best thing because it remains there once and for all. Okay, now let's move on. So we were at this point. Okay, right. So now we have this is the form of the covariant derivative. But now, what is in fact this this V mu? So if we just no, the small d. No, that lets be under the expression. No, the d under the expression is d prime. Yes, is d prime because you have v. No, hang on. So it's with v prime. if we have v prime, and we do have v prime, it's not written here, but it should be v prime. It should be v prime here. And in this way, this is d prime. Let me hang on. Yeah, prime d mu plus v mu prime. Yeah, so I did the same. D mu plus v mu prime and d mu. No, sorry. The d mu prime. The d mu prime is the d mu phi prime is what transforms as the field.
Okay, but you want the invariance, so it shouldn't.
Exactly. It should not exactly.
Just because of the v, because it has a prime.
Yeah, the v does have a prime, but not the mu itself. Not the mu itself. So we don't want it to have a prime here. Right. So what does it give us? So this. So let's define. Let's put the following, or put the v mu. So redefine v mu. This is just redefined. So what is the vector field that we know in the electromagnetic series? A mu. So if you redefine v mu in the following way, like I q a mu, and we are in a way using our gauge freedom to choose it in a convenient way. We choose it in this way, and doing so, then of course v mu prime is equal to I q a mu prime. We do this, and therefore we write our derivative, our not derivative, the covariant derivative d mu equal to d mu plus I q a mu prime minus I q d mu alpha x, which is equal to d mu minus I q a mu. And because now we are also going to recall that we had a transformation before. We know this a mu, it's equal. So we are using what we have defined as a gauge transformation on the fields, on the vector fields, on the electromagnetic field, let's say, plus d mu alpha x. And now I told you that plus or minus here is irrelevant. It is irrelevant at the level of the gauge sector, the vector sector itself. But now this signal here is going to be attached to this one here, or to the charge. Now the signs matter. Of course, if you flip one, you have to flip all of them. So using this, you have IQ a mu plus IQ d mu alpha x minus IQ d mu alpha x, and you see that these last two are just eliminated, so you end up with, using the vector fields that you know of the theory, that d mu is going to be d mu plus IQ a mu prime. And these are the covariant derivatives that ensures that sorry? Yeah, exactly. Without this, I can live without this background. So yeah, d mu plus IQ a mu. So this is what we get, and this ensures a gauge invariance. So the transformations are such that now we can say that d mu phi prime, this is equal to E to the minus I Q alpha X d mu phi and d mu phi conjugated prime is equal to e to the I Q alpha X d mu phi conjugated. That's equal. So with this, our theory, with this D L Klein-Gordon is a gauge invariant. U1 gauge invariant. U1 gauge invariant. So important to note that, and you should write, of course, with L Klein-Gordon written as G mu nu d mu phi conjugated. So I'm conjugating the full thing. D mu phi minus m squared phi dagger phi. And note that this definition of the covariant derivative, if I'm not wrong, to do this analogy, is that a nu is kind of this, the parallel to this affine connections in GR, and Q is the curvature, let's say. Q can have a geometrical interpretation of a curvature in this field space. If you don't have charge, Q is 0, so you don't have curvature, and you don't have the need for the covariant derivative. So Q is what is telling you if you have a charge or not. Does that transform as a connection? No, it's not the same thing. It's just a parallel. It's just a parallel correction to the derivative due to an imaginary curvature. Exactly. This is just a geometrical interpretation. I'm not saying this is curvature and so on. There are some arguments, more geometrical description of the field theory. Yes, it's true. Right. So now what do we need to go back and see what is the current? What are the currents now? What are the Klein-Gordon, the local Klein-Gordon currents? Yes.
But the Klein-Gordon Lagrangian is still non-gauge invariant. Only when you couple it with less.
Say again.
The true Klein-Gordon Lagrangian isn't gauge invariant.
You mean the one without the
without the new.
Why do you call it true? You call it minimal. No, that's the free. That's the free Klein-Gordon field with
an electromagnetic field. We have
exactly. When you couple, what you do exactly. If it's coupled, it's gauge invariant. If it's not coupled, it's not gauge invariant, and by definition itself. So the thing is self-consistent.
And I would assume that that's the same for the Dirac equation.
The same for the Dirac equation. It's we don't need to do the same job with the covariant derivative because it's the exact same thing, the transformation. So let's see how the Noether charges / currents, no, I mean currents, Noether currents look like. Currents look like. So we have the kinetic part. Now this requires a little bit more of workout, of course. G mu nu, so let me copy this to minimize this workout. Copy. Sometimes I forgot to use this feature of copying and pasting. So this G mu nu, of course, now I have to expand, and expanding, I get G mu nu, and I will just copy from here to be faster. D mu phi star, d nu phi. Of course, this is the non-interacting part. I q d mu a nu phi minus I q a mu phi star d nu phi plus now a square term, and this is the these terms are quite interesting. In fact, q squared, you see interactions here between the electromagnetic field and the scalar field. Quartic interaction between the scalar and the electromagnetic, and cubic interactions. So this is a quartic interaction. So two scalars, two vectors here. And this is a cubic. This and these two together is a cubic interaction. You have, I need a second field here. Somehow a field vanished here. Here it's the mu star, I guess. So I need to put this more like that, like this. And this is the a mu. So IQ the mu phi star exactly. And here you see like a triple interaction between a gauge field and two scalars. This is like in terms of Feynman diagrams, you can represent these two here as like a scalar, 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 and then a gauge. So a nu, and here you have phi star, here you have phi, and here this one here, you can represent as, in terms of Feynman diagrams, as like wavy line, a nu here, a nu. Of course, the Feynman rules should have also this tensor structure, so the structure of these indices. We'll discuss that also later on. So phi, here it's phi.
So this is sort of scalar QED.
Yeah, this is scalar QED, precisely. This is exactly what is being done here. Right, and now to get the currents, we need to start taking derivatives. So if we take derivatives of the Lagrangian, dl, d mu, dl d mu phi, this is equal to, and yeah, now there is some tensor. We need to, because we are using d mu and there are mu's here, so we need to be careful with this. Let me just say the result is, and I will just give one example: g mu nu d nu phi star minus I q g mu nu a nu phi star. Right, and this is equal. You can put things together, and you'll see that there is the covariant derivative, the structure of the covariant derivative here: g mu nu d nu phi star, and in the same way, dl d mu phi star is equal to g mu nu d nu phi. But let's just see, just because of the indices, and for those that are less used to this type of calculations, just to have an example how we should care about these indices. So what we do here is the following. So we are taking derivative d with respect to d mu phi, but let's call it alpha now generically. So what we are doing is a derivative d alpha phi of g mu nu, because we are not repeating g mu nu because d mu is already here standing. I'm using the indices, the same indices that are in the in the Lagrangian, mu phi. So here, below here, I have to define this as alpha. I have to write this as alpha. So this is the same as G mu nu d mu phi star, and now we have this that we've already seen before, the d nu phi, the alpha phi, which is the same as G mu nu d mu phi star, and this is now delta alpha nu, and therefore this is equal. You just apply the summation and you transform nu in alpha basically. So this is equal to G alpha mu the mu phi, but the indices that are being summed are dummy indices, so you can rename this. You can rename all these indices, in fact. So you can this is the same as renaming them as G mu nu d nu phi star, and this is what is written here to keep the mu's and nu's basically, because the index that is hanging is mu, so it's the index that is free. So I want to keep on calling it mu. Right now, right. So now for the kinetic part, so you already got this. Yeah, exactly. And now we can just write the currents. We can just write these currents. So our G mu is equal, as we've seen above, minus I sum. The sum is in phi and phi star qi dl d mu, and this is like psi equal the mu psi psi I. So we just apply, we just look into these two derivatives, basically, these two above here. So this, oops, it's this one and this one here. So the dLd d mu and dLd d mu phi star. And we conclude that G mu, in this case, G mu Klein-Gordon is equal to I Q G mu nu phi star d nu phi minus. So the main difference now is that we have big D's instead of small D's, or basically covariant derivatives instead of the partial derivatives. But let's this is still not the end of the story. This is the form of this of the Klein-Gordon. This is the Klein-Gordon current for the case of a gauge theory. But now let's see to at last see what are the sources of these currents. Let's take the derivative of the kinetic terms with respect to a mu, because you remember that we had L int before. We had minus J mu, nu for now, J nu, A nu. Remember this, right? We had this. So let's take, we know already what is this J mu, but let's take the derivative of the kinetic part of the Klein-Gordon exact dotted Klein Gordon with respect to the fields I knew. Because when I say the kinetic part, I'm talking about this bit here, of course, this bit here. That contains interactions, as you've seen. This kinetic part also contains interacting parts. In this case, with a field, with the electromagnetic field. So this is our L int before. Now is the kinetic part of the Klein Gordon, or it's contained in the kinetic part of the Klein Gordon Lagrangian. So, and this is a kind of a longish thing, but let's start. So, first, we have to expand. The Klein Gordon. The Klein Gordon, and it's expanded already. I should write it here. It's here, exactly. So let me copy and paste this. I would like to not have to take this Feynman diagrams there. Okay, copy. This is the kinetic part. This I put here. Okay, this is L Klein Gordon kinetic. Is this? So now we can start taking derivatives with respect to a mu, and this gives the following. So let me just make sure that the signs are correct here. There is, yeah, this is not a minus sign. I think this is coming from an equal that was above. So it should be like that. Let me see if it's correct above. Yeah, it's not minus. Right, so we have this, and now we take derivatives, and we have the first a mu, it's on the second term, so it's I, Q, G mu nu, d mu phi conjugated, phi, minus I, Q, G nu mu, because now we are the second derivative, so we have a mu, so we need to change. We have to take derivatives with respect to a mu, so there is a delta, and we need to change the names of this G of the indices. Phi star d mu phi plus Q squared G mu nu a mu. This is already in the quartic term. No, sorry. Yeah, it's the quartic still. A mu phi star phi plus Q squared G nu mu a mu phi star phi. Right. Now we can put IQ outside. Let's put IQ outside to get G mu nu d mu phi conjugated phi minus G nu mu phi conjugated mu phi plus minus, now it's minus IQ. In fact, let me just signal here. So I am now talking about this term here that comes here. Minus IQ G mu nu a mu phi, and again the same minus iq, and it's for the same reason as before. So this here, this one here, g nu mu, and u phi star phi. Right. So now we can pass one of these g mu's to be inside, sorry, one of these IQs. So this IQ here, I want to put this IQ here inside this because of the conjugation to get something which is IQ G mu nu G mu phi conjugated phi minus G mu mu conjugated mu phi, and now plus, oops, plus G mu nu I Q mu phi star phi. You will see where this is leading towards, minus G mu phi star IQ mu phi, right? And now you can already start seeing here the structure of the covariant derivatives showing up. So this is IQ So let's group the G mu nu and the G nu mu's together. This is D mu phi plus I Q I mu phi conjugated times phi minus G nu mu. So there is a minus there, G nu mu, and now D mu phi plus I Q I mu phi, and this is pretty much the so of course G mu nu is equal to G nu mu, so you can this is simply the same as G mu nu. So I kept them different to identify these two terms, to group them, and you can now write IQ J mu nu d mu phi star phi minus phi star d mu phi, which is, as we have already seen above, it's minus the Klein-Gordon current. Let me copy this for you to visualize below. Right, so IQ G mu nu, and then we have this the fields here. So the things are reversed. So this one, this one is here, and this one here is there. So this is equal to minus G mu Klein-Gordon. So this is interesting to note that that you take derivatives. So at last, so you take d L kinetic part, the interaction Klein-Gordon, with respect to the gauge fields in U, and you get minus G mu Klein-Gordon. Gordon-Klein, it's what I wrote. Klein-Gordon. So clearly now, the Klein-Gordon field is the source of the electromagnetic field, and you can further write the Ampere-Gauss law here that that holds here is the d mu f mu nu is equal to J nu Klein-Gordon. Of course, you can have more currents, like the Dirac current. And for the Dirac case, it's a lot simpler to see this. The Klein-Gordon one here was more complicated. The Dirac is simpler because if we now have a gauge theory for the Dirac Lagrangian gauge Dirac theory. So the Dirac Lagrangian is equal to psi bar I, for the same reasons as before, we put here d mu minus m psi, and we can expand this, and it's a lot simpler than the Klein-Gordon. So it's minus I gamma mu d mu minus q gamma mu a mu minus m psi, have this, and the derivatives of this Lagrangian, dl Dirac. So we are aiming at getting basically the currents here. This is equal to I psi bar gamma mu. Likewise, this dl d mu psi bar is 0. So it's trivial to get that the Dirac current is given by q psi bar gamma mu psi, as we have seen before. If you recall from what we have seen above, for the case of a global theory, it's the same thing. So where was it? So exactly. So there you go. So we had, look at what is on the screen. This is the case for a global U1. This was our global U1 scenario. Let me copy this. And now we compare to the case with the local. Let me paste it here for now. I can even keep it here. Let me. And this is the case of a local. I will change the color here, local, to distinguish. Local or gauge U1. So the thing is, so this is the same because in this particular case, the Dirac theory, when you take derivatives, when you calculate the currents, it does not depend on the derivatives of the fields. So if it does not depend on the derivatives of the fields, the global and the local currents are identical, which is the case here. But of course, being local, there is one difference, because if we say that this is a local one, then we can rewrite LD equal to psi bar I gamma mu d mu minus m psi minus j d, so the Dirac current, j mu d a mu. And this is only, in this case, only in the local slash gauge scenario.
In this case, since our function alpha was arbitrary, it should be a constant function. So
Sorry, so constant alpha, you mean?
yes, since we were working with an arbitrary function, one specific case is a constant function. So the scenario comes out from
The global scenario is like a particular case of the local. Like the global is a particular case of the local. Yes, exactly. Exactly. Yeah, but in that case, the mu's disappear.
But this happens for every kind of theory.
No, exactly. Not every kind of theory, indeed. But so here, in this particular case, you have like, once again, you can write the Ampere macro law, d mu.
That's why we associate the Dirac charge with the electric charge.
Yes,
Oh.
that's it. You associate the Dirac charge is like the electric charge of the. So if you specialize this to an electron, a muon, or a tau, or quark, or whatever, that's what our Dirac charge means. It's an electric charge. Well, and not only, it can be a weak charge. We will talk about charged currents, electromagnetic currents, and neutral currents in the case of the electric interactions. And this is our Ampere-Gauss law again. Again. So we have, if we now put together these two theories, so let's put together the Klein-Gordon and Dirac theories. If we put them together and we say, and this is again related to Hilarious discussion before, we have a theory with a fermion and a scalar, and they don't interact with each other. Let's say that they don't, but they have interaction with a minimal coupling to the electromagnetic field. They don't have to interact with each other because they can have different charges, and I will explain you why. This is again related to the discussion that we had before. So if I say that they don't interact with each other, so I observe nature, and nature is telling me that there is never an interaction between the phi Klein-Gordon field and the psi Dirac field that we have been talking about in a gauge E1 gauge theory. If that's the case, the Lagrangian, the full Lagrangian, would be like G mu nu d mu phi conjugated d nu phi minus the scalar potential, which contains the mass and the quartic couplings, plus psi bar I gamma mu d mu minus m psi. There is something else. What do you guys think there is here? So this is, I'm saying this, these two fields are charged under an electromagnetic theory, a local one.
So they should be
Exactly.
Cross terms.
That's the cross terms. I will come to that. But first, There is something else. So we have a fermion and a scalar, but we have something else. What else do we have? Yes, we have the photon, so we have a vector. And what is the Lagrangian? What is the Lagrangian of the free electromagnetic theory? Exactly. So minus 1/4 f mu nu, because this is, I'm telling that that you have the Klein-Gordon field and the Dirac field, and they have charged and the local one. So this implies the existence also of a gauge field. So I'm not imposing the gauge field. Let's say I'm not saying there is a gauge field and there are other things. No, I'm saying there is a local symmetry. Therefore, there has to be a gauge field there to make the theory. So the emergence of the gauge field is mandatory at this level. So it emerges. It emerges from the theory. And Osvaldo was saying something. Was saying cross terms. I mean cross terms. I mean between fermions and scalars, right?
Yeah.
So you could that the yeah was not very convinced, but okay.
No, that was it. That was it.
Good. So you could have even another interaction that we have discussed before, psi, phi, this Yukawa. Yes, exactly. But this one is only possible if the charges of the things, if the charges of the phi's and the psi's go together. So I'm saying that you have a certain cube psi. So it's minus cube psi, here is cube psi, and here is cube psi. And in phi, it's q phi. And this is clearly, the exponentials here clearly don't cancel out. You see, this term is clearly not invariant.
Well, unless q phi is 0.
Unless q phi is 0, but it's not 0 because it's coupled to the electromagnetic theory.
Yeah.
So this phi has a charge.
Couldn't you have a quadratic term though?
A quadratic term of?
Not quadratic, a quartic term.
No. Why can't we do this? Let me put with another color. Why can't we not do this? Let's count the dimensions of these things.
Yes.
3/2 plus 3/2 plus 1 plus 1. What is this?
But the coupling could have other dimensions.
The coupling you could put here a lambda, and now this would suddenly become allowed, but you would say our theory is not fundamental. This is an effective theory, and there is some lambda, some higher scale above the scale that I know.
How do we know? Just because it goes beyond a certain number, then it's not a fundamental theory, but an effective theory.
It's effective because this interaction does not exist at the renormalizable level, at fundamental level. It's a non-renormalizable. This is exactly, and this is non-renormalizable. So this is like the case of the same example of Fermi theory, where you have. I always give this example where you observe like for muons. Like the scattering of four muons. This is clearly non-renormalizable. So something got to be happening here. And later on, with the emergence of electric interactions, it was understood that what you have is like this. Mu, and then here a Z. But before knowing the Z, this is a non-renormalizable interaction. So it was 1 over lambda squared, where this lambda squared is the electric scale, is the Z mass scale, in fact. Lambda equals to mz, right? Then lambda squared mz squared. But this was non-renormalizable. But when you have a theory that is complete and everything is normalized, we can describe the exact same interaction with renormalizable vertices here. See? So here the vertices are normalized.
So there's really a mathematical definition.
Yes, exactly. This is really like you can always, with the up to dimension 4, describe a complete theory. Exactly. So the theory of everything must be renormalizable. That's the problem of not being able to quantize gravity, because it's non-renormalizable. So that's one of the problems. So, but coming back, so Q phi is non-zero. Psi bar and psi have the opposite charges. But of course, if psi and psi bar were different spinors, if I put here an index, so I and j, so or 1 and 2, then I could say that one of the charges is 0, and the other one is equal to that of phi. But that is not the case here. Here we are really saying that we have really only one side, and it's conjugated, it's antiparticle. So the theory, the theory that we have is what I'm going to try to highlight now. So with another color here. So the theory is this here. This is our theory, basically. Right, and there is another thing, interesting thing here that you notice. So V phi, you know what is, but look, in principle, you could write this term. So MA squared a mu. In terms of dimensions, it works, right? But let's see what gauge invariance does to this. If we now look into the, so this would be a mass of the photon. Yes, a Proctor theory. Mass for the photon. So Proctor-like theory. So if this is the case, let's then see what happens when we make the gauge transformation. So then this becomes m a squared of a mu plus d mu alpha x, the same alpha that is in exponentials of the scalars and fermions, a mu plus d mu alpha x, and this is equal to m a squared a mu plus a mu d mu alpha x plus a mu d mu. I'm expanding literally everything. Alpha x plus d mu alpha x d mu alpha x, and this is clearly different than ma squared a mu. So the big conclusion is that gauge invariance invariance forbids the photon from acquiring a mass. Acquiring mass. This is basically the consequence, the main consequence of gauge invariance. So at last, your theory would be, in terms of you can show that your theory, putting all together, can simply be written as L Klein-Gordon free plus L Dirac free theory plus L Maxwell plus L int with this L int equal to minus J nu Klein-Gordon plus J nu Dirac times a nu minus lambda over 4 phi star phi square. So the interaction, all the interaction terms are putting here. So when you write in terms of currents, the convenience is that you can isolate the free part from the interacting part. So you expand the covariant derivatives, and you can get this. For the case of Klein-Gordon, you can isolate all the interactions in a separate part. So this is if you expand, you can get to this point. Just to really to finalize, this is the absolute last thing now of this lecture, and we will leave the space-time invariance for next one. Is that so? This theory that there is, you can write the Feynman diagrams to this theory. So essentially, what we can do is, first of all, let's look to the Klein-Gordon. So we know that the Klein-Gordon current, how does it look like? And it is the following. So J nu Klein-Gordon is equal to, so where is, it was further above, so you can just copy this. I don't have to write. So where is it? It's here, exactly. Okay, but let me, I have the free theory, and then I have, yeah, but this is the current, so I need the current, right? But I want to write this in terms of free, exactly. So I need to, yeah, I need to expand this in another way. But I think I can do that in the following way. So from Klein-Gordon free minus J nu Klein-Gordon a nu, you get, so you can expand, and you get IQ. This is to understand what how do you read the Feynman rules. G mu, and now you get d mu phi conjugated a nu phi minus a mu phi conjugated a nu phi plus q squared g mu nu a nu phi. And when you write Feynman diagrams, you in momentum space. So in momentum space, we have d mu phi. You pass it. It's easy. You can look into the. This is a well-known formula, but you cannot look into the solutions of Klein-Gordon equation to once again conclude this. But doing so, this term. So this is. Let me just put this. Will be equal to minus q p plus p prime mu a mu phi star phi plus the same quartic thing. Copiar, colar here, right? And so, what are the Feynman diagrams here, and the Feynman and the corresponding Feynman rules? So I have screened out here. So we have these are the fields. So these are going to be the legs. And these are the fields. So here are going to be the legs. So we have two diagrams here already. So the red ones are going to be like this. So we have here phi star, we have here phi. This has a momentum here. There is a p prime momentum there. Then you have your a mu here, and this is equal. You can, this Feynman rule is the coefficient now that you get in the Lagrangian. And you should put always a minus I, which is coming from the path integral formulation of field theory. This is for another thing, but this minus I comes from an exponential. This is, I'm just teaching this in the form of how to read it directly from Lagrangians without going into quantum field theory, which would be a course on its own, let's say. And the green part is not momentum dependent. So this Feynman rule above is momentum dependent, as you see. Then we have another case. So the quartic interaction. It was slightly discussed above, but I will put Feynman rules here. So a mu here, a mu here, and the Feynman rule is equal. So let's read this. We have to take into account, I guess, some combinatorial factors here. So we have two phis and two a's. So actually the phis are different, but the a's are the same, and there is an interchange of indices there. So you have a factor of 2 here, 2i q squared g mu nu. So you see the mu nu dependence here, mu nu. So to contract with that. Now from the quartic part of the potential, so we have v quartic v phi star, which is also interaction part, is equal to lambda. So let me use the same. Is equal to lambda minus lambda over 4 phi star phi. I will expand like this. Phi star phi. So this one is not difficult to write. This is simply like this diagram we have been talking about several times. Phi star phi star, and the Feynman rule is minus I lambda, because there is a combinatorial factor that we need to take into account of these phis. And finally, there is the Dirac part. The Dirac part is so we also have this minus. So in fact, it's this minus j nu Dirac nu, which is equal to minus q psi bar gamma mu psi a mu. And the Feynman diagram it's also rather simple. So you have two fermions like that. So this is psi bar, which is going in the. So I'm defining time in this direction. So the bar and the stars go in the opposite direction of time. So here it should be like this, not there. A mu, and the Feynman rule is equal to minus I Q, the charge gamma mu. And that's it. So when you do calculations and you use these Feynman diagrams, you can build the Feynman diagrams and then you simply pick up the Feynman rules to do the calculations. And you can read at tree level all these rules from the Lagrange. Take into account some combinatorial 5%. But that's it. Okay, so let's stop here. And I think the other part of the lecture is going to be lost, at least the recording, but let's see. Okay.
We still have the notes, so it's not too big a deal.
Yes. At least the notes can help a bit.
Yeah.
I will actually stop recording now. I need to go to Zoom.
Yeah, I will leave because I have a class at 2 and I need to make lunch.
Please, yes,
Yeah.
please.
So
Go
see
ahead.
you next